Welcome to ATMOS 5000 Day 10. Our objectives for today are being pulled from Chapter 4, Sections 4.1 and 4.2 from the Stull textbook. We will be defining our humidity variables. We will introduce the Clausius-Clapeyron equation, which describes the saturation vapor pressure as a function of temperature. We'll talk about what controls the boiling temperature of a fluid, and lastly we'll introduce the concept of the lifting condensation level, which is essentially a way to predict the elevation of cloud base in an air mass that is lifted. In this lecture, we're going to start talking about the moisture variables of the atmosphere, how we describe how much water vapor is in the air. So you've already seen the mixing ratio, which is the mass of the vapor divided by the mass of the dry air. And using the ideal gas law, you could transform that into the density of the vapor or the density of the dry on these alternative forms. Depending upon the specific problem that you're dealing with, any one of these forms of the equation might be useful to you. I'd like to now introduce three other moisture variables. We'll start with Q, not to be confused with the Q in the first law of thermodynamics, but this is known as the specific humidity, and it's the mass of the vapor divided by the mass of the dry plus the mass of the vapor. So it's a slight modification of the mixing ratio, and alternatively you end up with the density of the vapor over the density of the dry plus the density of the vapor, or the vapor pressure over the total pressure, which is the pressure of the dry plus the water vapor pressure. I'd like to also introduce the concept of the dew point temperature, and clearly define the dew point temperature is the temperature to which an air parcel must be cooled at constant pressure to reach saturation. So you grab an air parcel, you stick it in a refrigerator, you cool it down at constant pressure, and the dew point is defined as the temperature at which a cloud will form in that chamber, because a cloud will form when the relative humidity reaches 100% or the air becomes completely saturated. You're probably very familiar with the concept of relative humidity, which is essentially a variable that is telling you how close you are to saturation. 0% relative humidity means that you have a dry air parcel. A 100% relative humidity means that you're completely saturated and no more water vapor can exist in the vapor form without condensing. So the mathematical definition of the relative humidity is the actual vapor pressure divided by the saturation vapor pressure, which represents the maximum amount of molecules of water vapor that can exist in the atmosphere at a given temperature, times 100 to turn it into a percent. Or alternatively, you could define this as the mixing ratio divided by the saturation mixing ratio, which once again represents the maximum amount of water vapor that can exist in the atmosphere at a given pressure and temperature. So the mixing ratio, the saturation mixing ratio, is epsilon, which is 0.622, times the water vapor, the saturation vapor pressure divided by Pt minus E sub s, which is approximately equal to epsilon times the saturation vapor pressure divided by the total pressure. So here we have a summary of the humidity variables that were discussed in the attached video. You might notice that I used a slightly different variable name for the mixing ratio in the video. I use using W instead of R. Some textbooks use W and some textbooks use R. The Stull textbook uses R, so that's what we're using for the humidity variable in this class. So we have the mixing ratio, we have the absolute humidity Q, and then we had from the ideal gas law, we have the density of the vapor, and then we also had the water vapor pressure as well. So now what we're going to do is we're going to be introducing the concept of saturation. So what we have here is a vessel that contains liquid water at the bottom.
It has solid sides and it has a solid top. And the initial condition here is that we put dry air in this canister above the liquid water. But what's going to happen is as soon as you start this experiment, there are there's liquid water molecules at the surface that have enough energy to break free from the liquid water, and they will evaporate and move from the liquid phase to the gas phase, which will increase the concentration of water vapor in the air. Eventually, all of those water vapor molecules that are in the air above the liquid water, they're moving around randomly, and some of those will have a collision with the liquid water surface and will stick. And that is the process of condensation. And the rate at which that happens is controlled in part by the temperature of the air, but also by the coefficient of accommodation, which is the likelihood that a molecule will stick to the surface once it comes in contact with it. So here we have an example where the system has been allowed to equilibrate to where the rate of the evaporation from the liquid water is equal to the rate of condensation, and we refer to this as a saturated system. The atmosphere, in this case, can hold no more water vapor because for every water vapor molecule that is added to the system through evaporation, one is going to condense out. And so at this point, we essentially have a steady state situation where the number of water vapor molecules in the air remains constant. So, by definition, the saturation vapor pressure is the maximum amount of water vapor that can exist in an air parcel, and it's controlled by one thing and one thing only. It's controlled by the temperature of the water. If you have high temperatures, then you have a lot of molecules at the air-water interface that have enough kinetic energy to break the hydrogen bonds that are holding the liquid water together, and you'll end up with a lot of water vapor in the atmosphere and thus a high saturation vapor pressure. In contrast, if you have a low temperature water in the fluid, in this case, then you aren't going to have a lot of molecules that have enough kinetic energy to evaporate, and therefore you won't have as many water vapor molecules in the air, and you'll have a low saturation vapor pressure. So in a given problem, if I'm given temperature, then I can immediately calculate the saturation vapor pressure for water vapor in that situation, because the saturation vapor pressure depends only on the ambient temperature. So here we have a graph showing how the saturation vapor pressure of water changes with temperature. And it's an exponential function. So at essentially a temperature of 0 degrees C, the water vapor pressure, the saturation vapor pressure, is 6.11 hectopascals or 0.611 kilopascals. And it increases exponentially as the temperature goes up and continues to decrease exponentially as the temperature goes down. This curve is described by the Clausius-Clapeyron equation, which we will discuss next.
So, one of the things that we want to do now is we want to be able to calculate what the saturation vapor pressure is as a function of temperature. So over here in the laboratory, we've done experiments to say, if we raise the temperature over a plane surface of pure water, as the temperature goes up, the water molecules, the water vapor pressure in the atmosphere above that plane surface of pure water increases exponentially. And we've seen that in the laboratory, and so what we want to do is develop an equation that describes this function so that we can have a functional form for the saturation vapor pressure as a function of temperature. And in order to do that, we're going to use the Clausius-Clapeyron equation. Now, in order to derive the Clausius-Clapeyron equation, which we'll do in a later thermodynamics class, we would have to introduce the concept of entropy. I'm going to skip that for now. We're going to start with the Clausius-Clapeyron equation and then move forward. The Clausius-Clapeyron equation basically says that the slope of this line is equal to the latent heat of vaporization divided by temperature times the difference between the specific volume of the vapor and the specific volume of the liquid. And you'll note, of course, that the specific volume of the vapor is much greater for a unit mass than the specific volume of the liquid. So in this case, we have the specific volume of the vapor and the liquid, and the specific volume of the vapor is much, much greater than the specific volume of the liquid. So this allows us to make an assumption here and simplify the Clausius-Clapeyron equation to dES over dt is equal to the latent heat of vaporization times temperature over alpha V. But recall that the specific volume of water vapor is equal to R sub V times T over this, in this case, the saturation vapor pressure. We can basically take that, substitute it into this equation, and you'll end up with dES over dt is equal to the latent heat of vaporization times the saturation vapor pressure over R sub V times T squared. You need to bring like terms on either side. You'll get dES over E sub S and LV over RV dt over T squared, and we'll integrate both of these from some reference temperature, where we have a reference saturation vapor pressure, to some temperature that's greater or less than that reference value, and we'll be able to get the actual vapor pressure at that temperature. So the integral of the left-hand side is now trivial for you. It's the natural log of E sub S of t over E sub S of t naught. And then the right-hand side, in order to do this, we have to assume that the latent heat of vaporization is constant. And we'll note that the latent heat of vaporization varies by plus or minus 6% over the temperature range of minus 30 degrees Celsius to 30 degrees Celsius. So what we're doing is we're introducing a significant inaccuracy into this equation by solving it analytically. But by doing that, we can just simplify the math, and we'll end up with the integral of t to the minus 2 dt. The integral of this is going to be t to the minus 1. So the evaluation is the natural log of E sub S of t over E sub S of t naught is equal to minus the latent heat of vaporization over R sub V times 1 over t minus 1 over t naught. And then to solve for ES of t, we take the exponent of both sides, and you'll end up with E sub S of t is equal to E sub S of t naught times the exponent of the latent heat of vaporization over the R sub V times 1 over t naught minus 1 over t. You'll notice that these are in different order than they are here because we distributed the minus sign inside the exponential. So this equation, which comes from the Clausius-Clapeyron equation, has a significant inaccuracy built into it, but it gives you the functional form for how the water vapor pressure changes with temperature. And that's reflected over here as the Clausius-Clapeyron equation that translated into the saturation vapor pressure as a function of temperature. And in this case, the temperature is in degrees Kelvin. But in the laboratory setting, they have actually measured this at multiple locations, at multiple times and multiple temperatures, and have come up with an empirical relationship based upon actual laboratory data that's much more accurate than that which comes from the Clausius-Clapeyron equation. And this fit to this laboratory data is E sub S of t is equal to the vapor pressure at T naught, which is usually taken as 0 degrees Celsius. So the saturation water vapor pressure at 0 degrees Celsius is 6.112 hectopascals. That's where that 6.112 comes from. Times the exponent of 17.67 divided by 243.5 plus temperature. And in this empirical fit for this function, the temperature must be in degrees Celsius. It's the only time this entire semester where you're going to be required to input a temperature in degrees Celsius into a formula, and so that's something that you need to do. So why use this equation over this one? This empirical fit is accurate within 0.5% throughout the temperature range of -40 to +40 degrees Celsius. And this equation, which comes from the Clausius-Clapeyron equation, is only good within about plus or minus 5% over that same range. So we have moisture variables, and we now have a way to actually calculate the relative humidity because we have a way to figure out what the saturation vapor pressure is as a function of temperature.
So from the video, you actually were able to see how the Clausius-Clapeyron equation was derived. And in the top here, we have the water saturation vapor pressure for liquid water, where we have our L sub V, which is the latent heat of vaporization, over R sub V, 1 over our reference temperature T naught, minus 1 over our actual temperature. And our constant out front is E naught, which is 0.6113 kilopascals. So you could do the exact same derivation, and instead of using the liquid water, you could do it for ice. And the only difference in this is that you have to use the latent heat of deposition as opposed to the latent heat of vaporization, because you're now doing a sublimation as opposed to an evaporation. And as a result, you're going to end up with a saturation vapor pressure over a plane surface of ice, which is less than the saturation vapor pressure over a plane surface of water. In the video, I provided one empirical formula for the Clausius-Clapeyron equation that is an empirical fit to laboratory data. And the Stull textbook uses a slightly different formulation for that called Teton's formula. And it's essentially an empirical fit to actual laboratory data. And it has a similar functional form to the Clausius-Clapeyron equation. And in this particular one, you use temperature in degrees Kelvin, and you have a constant B, and you have reference temperature T1, and you have a reference temperature T2, and you put the actual temperature in here, and you can get a very accurate estimate for the saturation vapor pressure as a function of temperature using this formula. Because the latent heat of vaporization and the latent heat of deposition are temperature dependent, and you saw in the derivation of these equations that we had to make the assumption that the latent heat was constant. These top two formulations can have significant error associated with them, which is why we often opt instead to use an empirical fit for the laboratory data, such as Teton's formula or the formula that was presented in the video. Other humidity variables which were discussed in the video include the relative humidity, which is simply a measure of how close we are to saturation, and the dew point temperature. And here from the Stull textbook, we have two formulations of how you can actually calculate the dew point temperature if you happen to know the vapor pressure E. And in this particular formula, T naught is our reference temperature of 273.15 Kelvin, and our E naught is our reference value of 0.6113 kilopascals for the reference water vapor pressure. And then you have RV and LV, which you should be familiar with at this point. In atmospheric sciences, we typically don't like to talk about relative humidity because it's not a true measure of the amount of water vapor that is available, because it really just defines how close you are to saturation. A high relative humidity indicates that you're close to saturation, while a low relative humidity indicates that the air is far from saturation. In atmospheric sciences, we're often concerned about how much energy is in a system. And you can have a very high relative humidity at a cold temperature and not have much latent heat energy available to the system, whereas you can, at a lower relative humidity at a high temperature, you might have much more latent heat energy just because of the exponential increase in the saturation vapor pressure as a function of temperature. So here we have three variables as a function of time of day. Temperature typically is minimum around sunrise, and that, let's just say it's 6 o'clock in the morning, and typically is maximum in the afternoon, in this case 3 to 4 or 5 p.m. in the afternoon. So you have the sinusoidal change in temperature throughout the day. And let's just say, for argument's sake, that the dew point temperature on this particular day remains constant. And what that means is that we don't have any evaporation or any condensation, which is changing the overall amount of water vapor that's in the air. And we're not advecting either higher moisture or lower moisture content air to a given site. So the dew point temperature is remaining constant on this day. And if we know those two pieces of information, we can then figure out exactly how the saturation vapor pressure is going to change throughout the day. Recall that the saturation vapor pressure is dependent on one thing and one thing only, and that's temperature. As the temperature goes up, the saturation vapor pressure goes up. As the temperature goes down, the saturation vapor pressure goes down. So it's exactly in phase with the temperature and is not impacted at all by the dew point temperature because it depends only on temperature. So, in this case, since the relative humidity is the actual vapor pressure divided by the saturation vapor pressure, and the dew point temperature is essentially telling us that the vapor pressure is not changing throughout the entire day, then the relative humidity in this case, when the temperature goes down, the saturation vapor pressure went down. So we're dividing by a smaller number, so the relative humidity has to go up at that time period. And then likewise in the afternoon, when the temperature goes up, the saturation vapor pressure went up. So you're now dividing by a larger number, and the relative humidity will go down. I'm not a wonderful weather forecaster, but I'm pretty good at predicting that the highest relative humidity at a site is typically observed at the time of the lowest temperature during the day. Let's do a different scenario. In this scenario, we have temperature that remains constant throughout the day. And this could happen if you had a thick cloud deck that prevented the sun from warming up the surface throughout the day. And just for argument's sake, let's just say that the dew point temperature was minimum in the morning and maximum in the afternoon. So in this case, what is the saturation vapor pressure throughout the day? Since it depends upon one thing and one thing only, that's temperature. Since the temperature is constant, the saturation vapor pressure must be constant throughout the day as well. So how will the relative humidity vary in the day where we have constant temperature but a varying dew point temperature? So in this case, the saturation vapor pressure remains a constant, but the vapor pressure changes as the dew point temperature changes. When the dew point temperature goes down, the vapor pressure goes down, and as a result, the relative humidity will go down. And in the afternoon, when the dew point temperature happened to be high, that would cause the vapor pressure to be high, which would cause the relative humidity to be high. So why is relative humidity a poor measure of atmospheric moisture? Because it depends on both temperature and the moisture content of the air. Unlike the dew point temperature, which only depends upon the amount of water vapor that is in the air. That's why we often like to use other moisture variables, such as mixing ratio or the absolute humidity or the dew point temperature, to actually characterize the amount of moisture that is in the air. So the dew point temperature is defined as the temperature to which an air parcel must be cooled at constant pressure for it to become saturated. An example would be opening the refrigerator door, letting air move into the refrigerator, and then you close the door, and the atmosphere inside your refrigerator will start to cool, and it will cool, and it will cool at constant pressure. And if you cool it down enough, eventually a relative humidity of 100% will be achieved, and that will be the definition of the dew point temperature. So high dew point temperatures occur when you have high moisture content, and low dew point temperatures occur when you have low moisture content. So a fluid will boil when the saturation vapor pressure is equal to the ambient pressure. So at sea level, where the ambient pressure is 101.325 kilopascals, you would have to raise the temperature of the water until its saturation vapor pressure, as measured by the Clausius-Clapeyron equation or Teton's formula, equals that sea level pressure. And that will only occur when the temperature is 100 degrees C. So if you happen to go to a lower pressure, as in moving to a higher elevation, the ambient pressure is reduced, and therefore the boiling temperature will be reduced as well, because you don't have to be as hot in order for the saturation vapor pressure to equal the ambient pressure. And the relationship between the altitude Z and the boiling temperature is given by this formula, which is found in the Stull textbook, where you have the latent heat of vaporization over the specific gas constant for water vapor, divided by A, which is a constant, plus Z over the scale height of the atmosphere, H. I'd also like to introduce the concept of the lifting condensation level. So here we essentially have an air parcel that is going to be forced upward, and as we force that air parcel upwards, the pressure will be reduced, which will cause the volume to expand, which will cause the temperature to decrease. As the temperature decreases, the saturation vapor pressure will decrease, which will cause the relative humidity to go up. And if you continue to lift this air parcel, the relative humidity will eventually equal 100%, and condensation will start to happen. And that will be the cloud base. So on the right, what we have here is a skew-T diagram. We have temperature on the x-axis and pressure on the y-axis. And we have an air parcel which has an initial pressure, temperature, and saturation mixing ratio. And over here in the blue, we have essentially the dew point temperature at that starting location. And recall that on the skew-T diagram, the brown lines in this case, the solid brown lines, are the dry adiabats, and the dashed green lines going up are our mixing ratio, R. So we have an air parcel. It has an initial temperature. In this case, it looks like about 30 degrees Celsius. And it has a dew point temperature of about -10 degrees Celsius. So if we grab our air parcel, which is the red dot at the surface, and we lift that air parcel, it's going to decrease at the dry adiabatic lapse rate, which means that the air parcel is going to follow this sloping solid kind of brown line, and its temperature is going to decrease with height. However, the mixing ratio, R, is not going to change with height as long as this air parcel isn't mixing with other air parcels, and that will be conserved with height. And eventually, the dashed blue line and the solid red line, in this case of your air parcel, will intersect at a location, and at that point the actual vapor pressure or the actual mixing ratio R will be equal to the saturation mixing ratio R sub S, and the relative humidity will be 100%. And at that point, a cloud will start to form, and we refer to that as the lifting condensation level. There are some equations that we can use to calculate the lifting condensation level if you don't want to solve things graphically. Here we have Z, which is the height of the lifting condensation level, is equal to a constant times the difference between the temperature and the dew point temperature. Or we can estimate the pressure of the lifting condensation level using the second equation. Or we can estimate the temperature of the LCL by using the third equation, which is equal to the actual temperature minus the gamma D, which is the dry adiabatic lapse rate, times the height of the lifting condensation level, Z LCL.